गौरव, गौरव, प्रीत कोई है क्या? गौरव, प्रीत.
Yes, I'm here, but the live stream is ongoing.
That's okay. Preet, can you call Vijay? Vijay,
Okay.
उनको आ जाना चाहिए ना, 8:20 हो गया.
हाँ सुरेंद्र,
He'll join at his slot.
क्या बोल रहे हो?
He would join at his slot.
अरे सुरेंद्र, ये वीडियो चल रहा है, वीडियो के ऊपर हमारा कन्वर्सेशन ऑन लाइव जा रहा है.
बोल रहे थे गौरव?
वीडियो जा रहा है और हमारा जो कन्वर्सेशन है ये भी लाइव जा रहा है सुरेंद्र.
Tu es trop grand pour comprendre des choses aussi petites. The future. How do you imagine it? Today, we're at the center of a tectonic shift in technology, where data, automation, and artificial intelligence inspire new forms of innovation and opportunities we can only imagine. Advancements in 5G communications, autonomous driving, cloud, and hyperscale computing are delivering a deluge of data, offering compute challenges for those most able to adapt. Strategic thinkers are embracing tomorrow's challenges today. The visionaries, the disruptors.
विचारसार परमा आद्यां जगद्व्यापिनीं वीणा पुस्तकधारिणीम् अभयदा जाड्यान्धकारापहा हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्
With this, now we'll proceed our program further. I would like to request our TPC co-chairs, Professor Vijay Raghunathan, to come and address the technical agenda of this program on the stage now. Professor Vijay.
Thank you, Preet. Just wanted to add a very warm welcome to all of you on behalf of my co-chairs, Professor Shaibal Mukhopadhyay from Georgia Tech and Professor Kamakoti from IIT Madras. And I'm Vijay Raghunathan from Purdue University, and we've had the pleasure of putting together the technical program for this conference. Just some quick statistics and an overview of the technical program. Starting off with the papers and the contributed or the submitted part of the program, we had 230 regular paper submissions this year to the conference, which is a very good number despite the fact that the deadline was bang in the middle of all the lockdowns and the unprecedented situation this year. Of this 230, 208 papers went into the review process. It was reviewed by over 60 TPC members and 45 external reviewers who worked very hard to provide good feedback to all the authors. In the end, we accepted 56 papers, which amounts to a 27% acceptance rate. We had a good mix of papers from industry and academia. We had 58 submissions of the 230 from industry. Predominantly, the submissions were from India. Almost 90% of the submissions were from India, 7% from USA, and 4% from other countries, including papers from Germany, Japan, Australia, Singapore, and the UK. We've had, as many of you have already listened to, we had 7 wonderful tutorials by leading academicians and practitioners over the past 2 days. We have a very exciting student research forum featuring 12 talks by PhD students and a user designer track as well, spread out over 2 days on 23rd, which is Tuesday, and 24th, which is Wednesday. Next slide, please. Can I get the next slide, please? Thank you. Headlining the contributed part of the program is a very complimentary and very exciting invited part of the technical program. We have 15 stellar keynotes from academia, industry, and government, and we're very excited to have these wonderful speakers present to us, sharing their perspectives and vision. We have 3 outstanding panel discussions, one on each day. Today's panel discussion is Decoding the Semiconductor Landscape of 2030. It's going to be moderated by Dr. Satya Gupta. Tomorrow's panel is about self-reliance in semiconductors for AI, moderated by Professor Subhashish Mitra from Stanford. And the Wednesday's panel is about the changing paradigm of VLSI education in India, moderated by Professor Abhay Karandikar, the director of IIT Kanpur. We have a special session on Wednesday on highlighted papers from the IEEE ACM Design Automation Conference in 2020. We're very excited about that session as well. We have invited talks from Intel and Circuit Sutra. And I would like to draw your attention to the awards ceremony, which is going to be on Tuesday afternoon from 3:15 to 4 p.m., where we will be presenting and announcing the Best Paper Awards, as well as some very special awards, including a Lifetime Achievement Award, as well as in an outstanding faculty award that we are very excited about. Next slide, please. And with that, I would just like to end with a word of thanks to, first off, all the authors for a very strong set of submissions, to our technical program committee members and external reviewers who, despite the times that we live in, volunteered their time to provide good feedback to all the authors. Again, many thanks to all the keynote speakers and panelists for sharing their vision and thoughts and making this an exciting aspect of the program. Our thanks to the session chairs and panel moderators for overseeing all the sessions. Many thanks to the sponsors, both the event sponsors and the technical sponsors and our partners. A big thanks goes to the members of the organizing committee, in particular the general co-chairs and the organizing chairs, for really putting in all the work at to organizing this virtual conference. It's not been easy, I can certainly tell you that, and so many thanks to them. And finally, to all of you, the attendees, for participating and facilitating the exchange of ideas and continuing to make VLSI Design the wonderful and exciting conference that it is. So again, on behalf of my TPC co-chairs, welcome to VLSI Design, and please enjoy the next 3 days of intellectually stimulating program. Thank you.
Thanks, Professor Vijay. With this, now I would like to request our steering chair, Professor Vishwani Agarwal, to come on stage and share his vision about VLSI Design Conference on the stage. Professor Vishwani, thank you.
My name is Vishwani Agarwal, and I welcome you to the VLSID 2021. I am a retired professor at the Auburn University. Although my slides show Guwahati, I am talking to you from Auburn, Alabama in USA. In the next few minutes, I'll give you a few facts about this conference. Most importantly, if you are attending it today, you are in the right place. This conference started in 1985 at Chennai. It has been held in 9 different cities in India. This is the first time in Guwahati, and it is also the first virtual meeting. For 2022, it is scheduled to be held in Hyderabad. This chart shows the number of papers selected at VLSID through their peer review procedure. Starting in 1985, the program expanded rapidly until about 2007, when stabilizing at about 80 papers. This is an international conference with participation from around the globe. It is always held within India. Offers tutorial by experts, paper selection through peer reviews, maintains the highest standard. All papers are archived in the IEEE Explorer. The conference makes extra effort to bring in selected keynote speakers. Please do not miss any of this year's keynotes. Every year, we may have a selection of the listed activities. I should mention that we enjoy a sister conference relationship with DAC, the Design Automation Conference. At this conference this year, Session 5B on February 24th will present 4 papers from the recent DAC as highlights of that conference. VLSI Society of India is our main sponsor. VSI was founded with the mission of promoting VLSI in India. Dr. Satya Gupta is the current president of the society. He and his team are responsible for maintaining the professional activities like this conference. Of course, This conference is organized by a large team headed by General Chairs Sudev Dasgupta and Gaurav Trivedi from IITs at Turkey and Guwahati. Both institutions have generously supported this effort, and we are grateful to them. Within the VLSI Society of India, a steering committee of 16 volunteers is responsible for maintaining the continuity of these conferences. I chair this committee, which is always looking for proposals, mainly for two conferences listed on the next slide. If you are interested in organizing one of these, you can send me a proposal giving the proposed location, facilities available, names of organizers, and tentative budget. In the recent past, the 24th International Symposium on VLSI Design and Test, that is VDAT, was held in July 2020 at Bhubaneswar in a virtual format. Next, the 34th VLSID will be held at Hyderabad during January 2022. I'm looking for proposals for future conferences, and here is my email. I hope to hear from you.
Thanks, Professor Shwani. With this, now I would like to request Professor Ajit Kumar Chaturvedi, Director, IIT Roorkee, to come on stage and give his guest of honor address. Professor Chaturvedi.
As one of the patrons of the 34th edition of the International Conference on VLSI Design and the 20th edition of the International Conference on Embedded Systems, I am delighted that after an year-long effort, finally this day has come when we are inaugurating these two conferences. It is a matter of happiness that two IITs, IIT Roorkee and IIT Guwahati, have joined hands to coordinate this event. Organizing a conference of this scale, an annual prestigious event, is not an easy affair, and I'm sure that both the teams at IIT Roorkee and IIT Guwahati have coordinated this effort very well. The operations have been very smooth and the teams had very good understanding of each other. During these times of the pandemic, which is almost fading now, it is a challenge to make the conference as lively and as interactive as it is possible in a physical event. The organizers have to put in special effort to make sure that the question answer sessions are as lively or the interactions are as lively as possible. Although they cannot replicate the physical experience, but I hope that we can try to come as close to the real experience as possible. And for the students, of course, this is a very, very important opportunity. The fact that the organizers have come forward to initiate fellowships, especially for students, so that they can do free registration, they can attend all the sessions. I think it's a lifetime opportunity to attend an academic research-oriented event, which also has very good industry participation. The students will have a lot to learn from the keynote lectures and also from the research papers, and maybe some of them will plan to take up a research-oriented career either in the industry or in the academic world. I hope that the takeaways for all the stakeholders, for all the participants of this conference will be better than the earlier editions, and I hope that the feeling is that the quality of papers continues to improve the way it has improved in the earlier years, and the level of participation amongst the different speakers and the different presenters also improves. I wish all the participants a great time at the conference. Thank you.
Thank you, sir. So with this, moving forward, I would request Director IIT Guwahati, Professor Sitaram, to come on stage and share his views about the conference. Professor Sitaram.
Namaskar. Welcome to VLS ID 2021. I'm very happy to introduce the 34th International Conference on VLSI Design and 20th International Conference on Embedded Systems, which will be held in virtual mode during February 20th to 24th of 2021. This conference is organized by VLSI Society of India, VSI, in association with Indian Institute of Technology, Guwahati, and Indian Institute of Technology, Roorkee. I am Professor T.G. Sitaram, Director, IIT Guwahati. I welcome all of you for this conference. This 34th International Conference in VLSI Design and the 20th International Conference on Embedded System is going to be very, very attractive conference. And the theme of the conference will be from the transistor to cyber-physical system for solving societal challenges. In this conference, the tutorials will be held on 20th and 21st of February, and the main conference will start from the 22nd of February and will be concluded on 24th of February. This is the 34th edition of the International Conference on VLSI Design and 20th International Conference on Embedded Systems. This is one of the prestigious international conferences held in India annually in the area of VLSI and semiconductor. We have to go online this time because of the pandemic, and I hope to see this international conference attracting large number of audience, as this is going to be in the online mode, which is also due to COVID-19. I'm impressed with the technical program with good participation from academia and industry. So there is also a large attendance of students through its fellowship program. And I also been told that there will be free registration and visit to all the session to generate interest among the student community in India. So I urge all the students to take the advantage of this free registration and register in large number and make this conference a successful conference. Due to the online mode, there will be its own challenges. So I request all of you to join early so that we can deliver, you can get the best mileage out of the conference. I wish all the best for the organizers, participants, and stakeholders, and in particular, my colleagues at IIT Guwahati and also the friends at IIT Roorkee. I congratulate them in organizing such an interesting conference online. Thank you. Namaskar. Good night.
Thank you, sir. So with this, moving forward, I would like to request Dr. Satya Gupta, President, VLSI Society of India, to come on stage and share his views about VSI and VLSI 2021. Dr. Satya.
Thanks, Preet. Good morning, everybody. And on the behalf of VLSI Society of India and ISA, I welcome all of you to the 34th edition of the VLSI Design Conference. As you know, this year we are doing this conference virtually, which gives us advantage to reach out to many more of you. And basically many of you are able to attend, which may not have been possible physically. On behalf of the VSI, I would like to thank the steering committee, organizing committee for putting together this great show in these tough times, as you all know. Just to share some things, India over last couple of years is going through a transformational phase in the area of electronics and semiconductor in all aspects, including R&D, design, and manufacturing. Government of India's policies in the manufacturing is basically creating a very vibrant ecosystem for all of us. So without further ado, I would like to thank all of you for joining us today and next 2 days for intellectual deliberations on VLSI, semiconductors, and embedded system. Thank you all for joining.
Thanks, Professor Satya, for sharing your views here. So with this, we are marching closer to the closing ceremony, and I've been asked to part of this closing ceremony. So there are many benefits being last in the queue, and there are some disadvantages as well. So I used to be kind of last in the queue during my college days with this 6+ feet height of mine. And the good thing was that all the questions used to be answered already before I used to land up. And so do today. Everything, I would say, the good, the bad about the situation we are in today due to COVID is being talked about. Professor Sudev, Professor Vijay, Professor Shishwani, Professor Chaturvedi, Professor Sitaram, and Dr. Satya Gupta already talked about the conference. But let me take this opportunity why this conference is special to me. So we started this conference 2 days back, 20th of February. That happens to be my father's birthday, auspicious occasion for me. And today, 22nd Feb, which happens to be the inaugural day of the conference, is again very special to me because this happens to be my wedding anniversary. So to me, this conference has brought up a lot of happiness, a lot of goodwill on this particular day. So let me move forward and I'll talk about some statics. My good friends in industry, they call me data-driven person. And yeah, in a role of a associate manager, I have to be data-driven. As associate lead, we need to really talk about numbers. We need to be really worried about the numbers of our chip, the area numbers, the power numbers, the clocking numbers, and obviously the dollar numbers. So I'll talk about a few of those numbers with respect to our conference. At VLSID, we have 33 plus partners, including our sponsors, technical partners, collaboration partners, and our sister conference. As Professor Vijay mentioned, we have 56 plus papers to be presented. We have 15 keynotes, 15 distinguished speakers on various panel discussions. We have special sessions, student research forum, user design track. If you put together all these numbers, other than our delegates, the representation in this particular conference is from more than 100, 150 institutions, academia and industry institutions. When we started this idea almost a year back, this was supposed to be a physical conference happening at IIT Guwahati. And due to COVID, we reached at a juncture where we thought that let's call it off this year because it's a humongous conference running 5 days with multiple parallel sessions. And we all got together in a virtual conference room. But seeing the passion of the team, they said, no, we'll go live, we'll keep on the tradition, which is running from last 35 years now. And we decided to make this as a virtual event. And here we are running the show. Then there was a suggestion, look, this is a virtual event. Why don't you make it a day conference? And we started thinking on those lines. But gradually seeing the entry of all the organizing team members and the number of submissions we were receiving, we said, look, we can't disappoint the whole VLSI community. We'll go ahead with our 5 days conference as usual. And yes, as you've seen, the number speaks. Certainly, there were challenges. We have to reschedule a couple of our submission lines because we were getting multiple requests across the globe because of the students not able to access their access to their institutions, their servers initially at the beginning of the lockdown. But finally, we are here with the complete agenda. Now let me talk about numbers. I did a post last night introducing our speakers for the day. It was almost midnight. I thought, okay, let the world know that we are inaugurating the conference. And look what happened. Within first 5 minutes, there were 60 views. Almost every 5th second, someone was viewing our update. You may call, look, in India we sleep late. But I would say that this is a wrong assumption. Because this being a global event, people across the globe, be it India, US, Europe, every time zone was eagerly following up on the updates of the conference. And that's what the number speaks. So with this, I would like to move forward with our agenda. As you can see on the screen, that we have a bunch of sponsors starting from different categories. We have our sponsors, Silicon sponsors, Cadence Design Systems, Intel, Micron Technologies. Our Platinum sponsors, Xilinx, Siemens EDA, Analog Devices, Circuit Sutra. Our Gold sponsors, ST Microelectronics, NXP Semiconductors, Moschip, and Altair. Our Silver sponsors, the biggest queue, 5 in a row, Synopsys, Global Foundries, Qualcomm, MediaTek, and Smart SoC. And last but not the least, our bronze sponsors, Insemitech and HCL. So I think this slide is more filled with colors if I compare with the previous years. Though when we started, we knew that the world is in trouble, so do you can see still our supply chain is in trouble. But I really thank to each one of these sponsors to be part of us. And without them, this show was not possible. As like every year, it's a tradition that all these reputed technical societies of the globe, they are our technical sponsors. So same, this year again, we have our technical sponsors from IEEE, CAS, CEDA, Computer Society, TVLSI, SIGDA, CPS, ACM, and SIGMicro. We have some special collaboration partners which really gets us a new value add in the whole ecosystem. I'm really honored and thankful to Ministry of Electronics and IT, MIT Government of India to be our collaboration partner, along with IIT Guwahati, IIT Roorkee, Indian Electronic and Semiconductor Association, and TechSagar, which is an initiative by Data Security Council of India. And as like every year, our sister conference, DAC, this year we have more bigger partnership with DAC. We are going to have a special session on DAC, thanks to the DAC team, to extending this bigger partnership for this sister conference. So thank you. Thanks to all the technical sponsors, our collaboration partners, and our sister conference. So with this, we are marching towards the agenda of the day. As you can see on the screen, this is the agenda for the first half. And you can see the list of distinguished speakers. And I really don't want to hold back between the audience and the speaker to come and interact. So before I proceed further, before I invite our distinguished speaker on the stage, I would like to mention that This is going to be a virtual interaction between the organizing team, between the conference stage and the audience. So each one of you can write or post your queries on the Q&A part, which you would see on the right bottom. And at the end of the talk, I'll take up those questions, obviously based upon how much leg room in terms of time we have, and I'll request the speakers to answer those questions. So with this, without any further delay, I would like to call upon our inaugural day distinguished speaker on the stage. So these are the speakers for the day. As you can see, we'll hear from each one of them as we proceed further for the day. And with this, I would request our first inaugural day keynote speaker, Mr. Ravi Shankar Kuppuswamy, to be on the stage. Ravi Shankar Kuppuswamy, he is Corporate Vice President of Intel Data Platform Groups, General Manager of Custom Logic Engineering, Intel. He is responsible of leading global organization which develops and deploy differentiated end-to-end custom logics. He is a well-known face in the industry. Ravi Kuppuswamy served previously as Vice President in Programmable Solutions Group, which is PSG. He joined Intel in 1996 as an unlock design engineer, and subsequently he held multiple positions in technical leadership and management at Intel. He's been associated with 5 generations of Intel products. In 2008, India's National Association of Software and Service Companies, they awarded the Dinnington program of Intel, which was led by Ravi Kuppuswamy. So without any further delay, I would like to request Ravi Kuppuswamy to come on the stage and share his vision on digital democratization driving social change. Ravi, over to you.
Thank you. Should I be sharing my files directly?
Yes, Ravi.
All right. Let me know when you guys can see this, okay?
It's yet to show up.
How about now?
Great, you're good to go. Kindly move to full screen mode and we are good to go. Thank you.
How about now?
Yes, Ravi, we can see your full screen slides. Thank you.
Can you see? Can you hear me clearly as well?
Yes, sir.
All right. Let me go ahead and start my video as well so you can see me too. Hey, first, thank you very much for inviting me to present in your esteemed forum. My topic for today is going to be on digital democratization and how that drives social change. Thanks for the kind introduction. And what I'd like to do is first maybe start by walking you all through what would be a definition of digital democratization. And actually, I've taken a little bit of liberty here in kind of making up this definition. It's essentially the process by which access to digital technology rapidly becomes more accessible to more and more people. And through this, essentially in the hands of all people around the world, the ability to go ahead and compute and have digital technology at their fingertips. So with that, let me just say, hey, the first phase of this digital technology started about in the 1980s, where we started to use computers for the first time, where we started to digitize everything. And when you look from the 80s to the 2000s, it was what we call the PC era, where over time, there was 1 billion people connected on the internet. through PCs. Now, if you were to look at India from that standpoint, actually India had a slower start in the PC space. I would think about 50 KU to about 1 million units of PC sold per year towards the end of 1999 or so. An average PC, about 40K rupees. Connectivity, not all that great, 9.6 to about 33 kilobits per second. But overall, you would like to think of it as a slow ramp of PC, high data cost for broadband, limiting penetration to maybe about less than 5% of the total population. If you were to look at the next phase from the 2000s to 2020, we got about 10 billion cloud connected devices. The mobiles were taking off, and more things were getting on the cloud. And suddenly, India gets on a fast track. There's a fast ramp in mobile phones, about 150 million units of phones sold per year. Average price of the phone, 12K. And then essentially, you have the lowest data cost per bit on the planet in India, with an adoption rate greater than 65% population having some kind of phone. That's phenomenal, given the fact that that equates to about 850 million people. So when you fast forward this and look and understand, how does this compare to everybody else in the world? Clearly, with 850 million people, the only nation ahead of us in that stage is 950 million in China, and the US had about 405. But you can clearly see that this is a massive number of people for whom data is available at a fingertip with a touch of a screen. Now, what happens from here? When you move into this next phase, what we're really talking about is intelligent everything. About 100 billion intelligent connected devices is going to have a distributed intelligence for everyone. And then this is where people are saying you could go from anywhere from petascale compute, 10 power 15, to zetascale compute at 10 power 21. When you have that kind of power of compute, which was originally accessible to a few that could afford supercomputers, now widely available to masses, changing lives in a more pervasive way, then you've truly achieved what I call as digital democratization. Now, let me just walk forward and say, in the last 5 years, we have not yet even reached what I call as the intelligent phase, 100 billion devices. Let's say in the cloud and mobile era, I was talking to a few colleagues, and then they gave me some pointers to some examples, because since I was going to be talking here, I wanted to try and understand, are there examples in which, even in the cloud and mobile era, have we fundamentally changed society, and what this could mean for the future? Here's an example of two villages. Okay, one is Churni in Maharashtra and Sahibganj in Jharkhand. Two what you would call as classic rural villages, where forget about anything related to the internet, even having a few PCs in these villages was very scarce. And whatever PCs that existed was actually in what we would call as these service points, this common service point. And clearly connectivity was very flaky. Now, in this space, here is a case where colleagues of us in Microsoft Azure partnered with Air Jaldi to create one of the first penetrations of broadband network with this tower that you see in this village, leading to essentially people like Akash Alokar, who owns one of these common services points, to suddenly provide e-services in a more stable manner, not just to his village, but also to the villages around. Suddenly you can start seeing that people are able to go ahead and access technology, even though not every one of them has one, but even if there was one close enough to you, the availability of that technology is starting to change the way they use it. It could be towards filling their tax forms, towards actually having an ability to get a license, actually having an ability to access services that the government wants to provide, but is unable to provide because of the last mile. And you can see it has also changed the way in which people get more jobs. Here's Asha Kumari, who actually was an educated computer science engineer, found herself as the network operator head for Air Jaldi, providing services in Sahibganj. And very soon, she's enabling multiple villages in the area have this access capability to the services that needs to be provided. And this is not just a story about technology reaching all of these people and having a way in life. It is also a story about empowerment, empowerment of women, empowerment of people who are marginalized in the society to suddenly play a more active role, both in contributing to technology and also enabling all the people around them. So what was so special about this? The special aspect of this was the fact that broadband network that was so difficult, more expensive to reach some of these ruralmost areas, suddenly on the cloud platform, Air Jaldi was able to go ahead and provide software services. It was one of the first examples of running their entire services on the cloud. So here's another example here related to precision agriculture using AI. Nominally, you see that chart on the left essentially is the rudimentary way of actually predicting when to sow crops, when to harvest them, when to water them, when to irrigate them, when to actually de-infest them from pesticides. So if you really look at it, and if they got it wrong, their yield went down tremendously. Their ability to actually access that piece of data required AI running on the cloud, again on Microsoft Azure, collaborating with ICRISAT and UPL, providing a capability where they took in data for the last 25 years of climatic conditions in the area, including moisture availability indexes, and created a model, an AI model, which was then only from the farmer standpoint was an actual text to their phone saying when they should be sowing their seeds, when should they be actually understanding and disinfecting their plants, what kind of disinfection should they be really be using, and more importantly, identifying and enabling them with what kind of diseases there could be. And all of this in collaboration, not after the fact, but actually using an AI model before the fact. And when it was all done in 2017, the 1,000 farmers who actually participated in them approximately saw 30% better yields at the end of the season, which is phenomenal in their situation. And then they also got better pricing, knowing where they needed to go take their goods, as opposed to going 30 miles in one direction, going the other direction to actually get to the markets that they need to be in. Here were two examples where you saw technology changing society at the basic level. Now, what is it in it for all of us here as representatives of their organizations or in academia? What are we doing to go accelerate this kind of societal change? The example that I showed, Intel XPUs actually power AI in Microsoft Azure. That's why we are very closely involved in collaborating with them to have the best CPUs and FPGAs on their Microsoft cloud. How can they actually go ahead and use it in a fashion in which it is no longer about just the hardware. Here is a case where the transistors no longer are about just a CPU or a GPU. It could come in forms of CPU, GPUs, AI chips, FPGAs, interconnect chips, memory chips, and that is just the bottommost layer. Above this layer are the things that we do in drivers and OS and virtualization to create the packages that we need to go ahead and create. To the levels in which the systems, which include our middleware frameworks and runtimes and libraries, leading eventually to the high-level software stack, which provide the services and solutions that these people feel and touch. This is going to be the engine that drives us from today, as we look at supercomputers as petascale, to zetascale compute, zeta as in 10 power 21. And people would think, hey, maybe he's smoking something. Let me just walk you through some of how this is possible. If you really look at it, the lowest levels of the hardware today in our supercomputers are around petascale, and we are actually building today something that fits in one chip. When you multiply that with the different architectures, the interconnect, where you could get 4x the improvement there, or the memory, where you can get another 4x the improvement there. And by the time you work up the stack all the way to the software stuff, you would be running into easily the exa and zeta scale compute capability. Now, this particular chart is very important and pertinent to India from one sense. Is India is home to nearly 6 million software developers, which is a huge percentage of the total number of developers. And as we abstract these levels of layers up, it has the ability to go ahead and service this, not just for India, but for actually the entire world. And then that is why it is super important for us to go ahead and look at these problems, not just as a hardware stack or some layer in the middle, but as an entire solution that's driven by XPUs. Let me talk a little bit about opportunities here. Intel's providing 3 basic opportunities in this space for India. I'm going to tell you a little bit about Intel One API that abstracts the different layers so that no longer do you need to be so prevalent and understanding of the lower level hardware. You would have the ability to go ahead and access all that compute at the highest levels by Intel One API. We also have an Intel FPGA University for those folks who need to go get down and drive into the details and understand how this works so that they can work their solutions through it. And then we also have an Intel India startup program. And I'm just going to quickly walk through each of these very quickly. One API is an industry level initiative where we have a unified programming model to simplify the development across these diverse XPU architectures. It is unified, simplified language and libraries for getting the parallel nature of our compute accessed. We essentially are doing this without compromising on any native high-level language performance. And we are trying to do this by keeping it open industry standards and specifications. Essentially, the ability to go ahead and access all of this capability at the highest levels, or if you choose to do so, going lower and lower levels. Our FPGA University program has, I won't go through all of it. We have over time in 2020, 12 institutes, lots of faculty, and one case plus students. We have done 2 FPGA specific focus ones in other areas as well. And then we have partnership in terms of startups, IP, ecosystem development, so that we can get a whole class of people working on these XPUs, inclusive of FPGAs here. And then last but not the least, our startup program. We want to give people access to the technology, access to the ecosystem, access to the ability to get the scale that they desire and the visibility that they desire, and providing mentorship by the best at Intel. I won't go through these. There are some success stories across a variety of platforms, from automotive to healthcare to safe compute, all of which are super important in the growth that we seek. So this is my last foil, and I want to end my talk by essentially saying we are finding accessible compute that is leveling the playing field. Today's XPUs are going to power a ZScale India. You can see a connected India where you could have 50 supercomputers, each with greater than 20 exaflops, distributed and connected every 160 kilometers, will provide a compute capability bar none. Our ability to collaborate on solutions development with this infrastructure in place to innovate and drive the social change that we all wish to see. And here's a classic example to show that, hey, digital democratization for a self-reliant India, an Atmanirbhar Bharat, which is extremely critical as we enter into the intelligent phase. And I fully see this happen between now and 2025. It could be revolutionary in taking us forward. Thank you.
Thanks, Ravi, for this insightful talk about the digital decarbonization. So we have a lot of questions already in line, and it's difficult for me to pick and choose, which one to be presented to you to answer. But in the interest of time, what role you think Intel as a huge organization with all this digital expansion focus would play for a self-reliant in India?
As I said, Intel clearly is the driver of Moore's law for the last several decades. For us to have the kind of compute that I talked about, going from peta to exet to zetascale compute, and in this time and age, to essentially go ahead and provide that kind of compute, Intel is innovating across the different XPU architectures, whether it be a CPU, a GPU, an FPGA, memory, interconnect, AI acceleration. All of these capabilities are going to be important in driving the diverse kind of workloads that are going to be required to accelerate in tomorrow's world. The data centers of tomorrow are going to require a combination of all of this. But it's not Intel alone. Intel, in collaboration with all of the folks here on this call and more, are going to require to develop solutions built across. It's not just about the underlying hardware, as I showed, across the different layers that are required, leading to the important aspect of touching and feeling every person on this planet. And that actually happens to be Intel's vision as well, which is to truly touch and make a difference on every single person on this planet.
Thank you. Thanks, Ravi. So I'll just pick up another question for you. And as I said, it's difficult to, get all the questions answered from you. The row is huge here. You mentioned 1980, digital everything, 1990, network everything, around 2010, mobile everything, and now cloud everything. What would be your insights about, say, 10 years down the line, 2030? What everything?
Like I said, it's intelligent everything. If you saw the fall, it's into every device, whether it be, let's just say, for example, whether you're in the cloud, you're in the network, or you're at the edge. It's no longer going to be possible or practical to essentially do a compute in one place, go to the cloud every time you need to get data and bring that data back and then use it. Anything that is going to be required is going to get computed locally, okay, at the edge, at the devices, near the thing, so you're not going to be reliant on back and forth transfer of data. So when you have that kind of capability, suddenly all of these devices that are going to be there are going to be intelligent. And when they become intelligent, essentially meaning their ability to not just be dumb sensors, they're going to be intelligent sensors. They're going to be intelligent devices. They're going to talk to each other. They're going to communicate with each other. They're going to devise solutions with each other and provide the access that every person requires when they need it, where they need it, and not have to wait for it. And that's going to change everything. So if and tying it back to India, if India wants to be in the forefront of this, our ability to go ahead and truly ride the wave, which I believe it can, because of its not just its software population, but inclusive of its software population, go make sure that we can capitalize on this intelligent phase that's going to happen in the next 5 to 10 years. And I truly believe that's going to be game changing, and that game changing aspect is going to be fundamentally touching everybody. And then when you touch everybody, then you're going to make a difference to everybody's life.
Thanks, Ravi. Thanks for your insightful talk. And to the person who asked this question, it's going to be intelligent everything 10 years down the line. So on behalf of the conference organizing team and on behalf of the VLSI Society of India, kindly accept a virtual token of appreciation from our side. Thanks a lot.
I'm happy, and thank you for the opportunity. Thank you.
We'll be shipping you a physical token of appreciation post the conference, and looking forward to see more collaboration with CLE Group and Intel and all. Thank you. Thanks, Ravi. So with this, we'll move forward. I already see Professor Beldaly with us on the backstage. And it's a true privilege and honor to introduce Professor Daly today. So Beldaly, he joined NVIDIA in January 2009 as chief scientist after spending 12 years at Stanford University, where he was chair of the computer science department. Daly and his Stanford team, they developed system architects, network architects, signaling, routing, and synchronization technologies that is found in most of the large parallel computers today. Daly was previously at Manchester Institute of Technology from 1986 till 1997, where he and his team built J machines and the M machines, experimental parallel computing systems that pioneered the separation of mechanism from programming models and demonstrated very low overall synchronization and communication mechanism. From 1983 to 86, he was at California Institute of Technology, Caltech, where he designed MOSIM simulation engine and torus routing, which pioneered wormhole routing and virtual channel flow control. He's a member of National Academy of Engineers, a fellow of American Academy of Arts and Science, fellow of IEEE and ACM. He's being awarded multiple recognition and awards globally. He has authored more than 250 papers. He's having 120 plus patents issued on his name. He has authored 4 books. Daly has received bachelor's degree in electrical engineering from Virginia Tech, master's in electrical engineering from Stanford, and PhD in computer science from Caltech. He was a co-founder of Video Communications and Stream Processors. So truly an honor privilege to host Professor Daly today with us. He'll be talking about the future of computing, the domain-specific accelerator, which is a buzzword in all the technical group these days. So with this, I welcome Professor Daly on the stage. Over to you, sir.
Well, thank you very much. Let me share my screen here. I don't get a monitor. I hope you are seeing the right slide.
Yes, we could see the slide and we can hear you well.
Good.
Over to you.
So I'm very excited to be here. Thanks for inviting me. It's quite an honor to speak to all of you. And I'm also very excited about the topic. It's a very great time to be a computer designer because we're not just tuning the same old CPU anymore. we're designing very different things and getting huge performance increases by doing so. I can only touch on some of the highlights in this talk. So let me refer you, oh, my slides are not advancing, hold on a second here. Let me refer you to a CACM article that I published this past July on domain-specific hardware accelerators, which can give you some of the details I'm not going to have time to go over in this talk. Fundamentally, the problem we're trying to solve is to add more value to many endeavors of humans in this world. And the way we do this in the computing world is it starts with faster computing. Typically, whatever computer we have today, people have it completely filled. There's no headroom left. You can't add any features. You really can't innovate very much because you need more horsepower to innovate. And you need a faster computer to allow you to get some headroom so that you have room for better algorithms and for more data to add more value to the ultimate enterprise. And so we really have a need to continue to deliver the performance per watt that the world has become accustomed to over the scale of computing going back to the 1970s. And for many years, this was delivered via process technology according to Moore's law. But process technology isn't helping us anymore. Moore's law is dead. This was declared in the Wall Street Journal a little while ago. A more authoritative source in my mind is the textbook from two recent Turing Award winners, John Hennessy and David Patterson, who show, back in the wonderful days of the 1990s and early 2000s, that we were scaling computing at 52% per year, and now it's almost flat at 3% per year. The good news is we can continue to provide the performance and efficiency that the world has gotten used to for computers through faster accelerators. And I'm particularly happy about this because I've been building fast accelerators since 1985. Some of these were mentioned in the intro, the Mausam simulation engine and Mars Accelerator did simulation. There are a number here that did signal processing and graphics, some that did neural networks like EIE and SCNN, and some that do bioinformatics. I made many mistakes over the years since 1985 and learned a lot about what makes accelerators work. And it's really kind of summarized on this one slide. Accelerators get their advantage due to specialization. That's why we call them domain-specific accelerators. By creating data types and operations specific to a particular domain, we can do in one cycle what often takes tens, hundreds, or often even thousands of cycles on a conventional CPU. And we can get 10 to 1,000 times, sometimes even larger efficiency gains. I'll give some examples of that soon. But the specialization really gets that efficiency. It doesn't really get that much more performance. But by getting that efficiency, it then enables the next step, which is to put down lots of copies of whatever that accelerator is and do many operations in parallel. Not this, the model we've had of computing via CPU is a single operation at a time taking place. So now we can get many operations going on simultaneously, and that's where the real performance comes. But this ability to get this very high level of parallelism was enabled by the specialization. The next step is to optimize memory. It turns out most algorithms today are balanced on a conventional machine, and if you make the computing part go extremely fast, they become completely memory limited. So we have to both tailor the algorithm to use memory more efficiently and tailor a memory specifically for the algorithm to get the performance we need. A lot of the gains of specialization are really reducing overhead. I'll talk about this a little bit more in a few slides. And almost always the algorithm has to change. If you take some dusty DAC program and try to accelerate it with hardware, you'll get a small gain, typically because you'll wind up with it being memory limited very quickly. You typically have to innovate on the algorithm as well as the architecture to keep it balanced as you specialize. So let's talk about the first of these first. I'm losing mouse here. Specialized operations. And the example I'll use to illustrate this comes from our Darwin accelerator that accelerates bioinformatics. The core of many different bioinformatics applications, whether they're de novo alignment, whether they're reference-based alignment, whether they're whole genome comparisons between different species, at the core of all of those is dynamic programming, an algorithm known as the Smith-Waterman algorithm due to the particular cost functions used in the dynamic programming, where I compare one string, this is a string of bases, we'll call the reference sequence, to a query string. What I want to do is I want to come up with a minimum cost edit of the query string into the reference string. And that it may include matches, say G matches G here, mismatches where I get charged a penalty, say if G doesn't match C down here, inserts, if I wind up inserting several things into the, actually this inserts are vertical here in the query sequence, and deletes if I delete things that are in the reference sequence but not in the query sequence. And the cost for computing the minimum cost sequence at each point is given by these recurrence equations, where I have a affine cost for inserts and deletes, and then a particular substitution cost for matches and mismatches. And carrying out these recurrence equations on a CPU takes 35 ALU operations and 15 loads and stores, 37 cycles, and on a 14 nanometer Intel Xeon, this takes 81 nanojoules. We designed this in a 40 nanometer technology where all of this takes place in a single cycle. It takes 3.1 picojoules, so it's a 26,000 times gain in efficiency. And in fact, all of the math takes 300 femtojoules. The remaining energy, in fact, the bulk of the energy is doing a single write for each cell, where we store the traceback pointer. So we can, once we find the minimum cost, we can trace this path back, trace the path back and find the edits. So for the logic itself, we're actually 270,000 times more efficient than a CPU in 3 generations newer technology. How can this be? Well, the answer is that it's easy to do this in part because CPUs are so inefficient. During that steep climb in the 80s, 90s, and early 2000s, there was a real push to make CPUs faster at the expense of efficiency. Because the technology was improving so rapidly, there was a huge premium on not having to recode things in a parallel way. And so if you could make a CPU faster by speculating, running instructions out of order, predicting branches, all sorts of things that have huge energy costs, it was worth doing. And as a result, if you look at a modern CPU, and this, the result I'm quoting here from a particular paper is for an ARM A15. It's not even a particularly high performance CPU. A state-of-the-art x86, or even one of the more modern ARM cores, is far higher overhead and far higher performance, because those two go together. And what you see is most of that energy goes into the instruction fetch and decode and predictions and reorderings and the like, and then unwinding them all if you get it wrong. And this little red dot here for a 16-bit add instruction is the actual payload. It takes 32 femtojoules to actually do the add, and 250 picojoules to basically do all of the overhead associated with the add. So a lot of what's going on with the special purpose architectures is getting rid of the big blue area here and just doing the add. And that by itself, gives us a 10,000 times gain. Specializing around data types and algorithms gives us more above that. So the basic sequence that goes on here is by specializing, we get efficiency. We get to build a processor that takes only, a few hundred femtojoules to actually do the logic and a few picojoules to do the logic plus the one memory operation. That efficiency then lets us build thousands of these processors in a relatively small chip, consuming a relatively small amount of energy. And those thousands of processors give us performance through parallelization. Let's see how that works for the dynamic programming engine. Here are recurrence equations. We build these recurrence equations into these processing elements that are connected in a systolic array. Each of these elements is computing one square of the dynamic programming matrix, but we can have an array of them. Our actual arrays are 64 PEs. I didn't draw that here because it would have been difficult to see on the slide. But imagine these 4 are 64, and they compute an anti-diagonal of the dynamic programming matrix each clock cycle. And as they compute that anti-diagonal, they write the traceback pointer for the square they just computed, the cell they just computed, into these local SRAMs associated with each processing element. But that uses only 64 processing elements. Our gain in efficiency gives us ability to build way more than that. So we exploit outer loop parallelism, and we actually do 64 query sequences simultaneously. And within each of those, we do 64 cells of the array at the same time. So the peak parallelism is 4,096, multiplied by that 37 times parallelism. It turns out, because of startup and shutdown overhead at the start of each problem, we don't quite get the peak, but we get a pretty good number. And the total speed up here is 150,000 times on just the dynamic programming part of the algorithm. Now, it turns out that if we had done this, we would have been killed by Amdahl's law, because the conventional way people did genome alignment when we started doing this was dominated not by the dynamic programming, but what was called the seeding stage or filtering stage of the algorithm, where you take a number of seeds and you look up in a database the likely locations of matches based on those seeds, and use that to then do a relatively small number of alignments. So at the time we did this work, the state of the art in long read alignment was a software program called GraphMap. It's since, with the invention of Minimize, it's since evolved into a program called Minimap, but they're essentially the same for the purposes of this argument. And in GraphMap, it spent an enormous amount of time in filtration. The filtration is shown in blue here, and almost no time in alignment. There actually is a little bit of red at the right side of that bar, but it's small enough that it's almost in the noise. And it did this because alignment on a CPU is so expensive, you want to minimize doing it. So you'll spend an enormous amount of time doing filtration to avoid doing alignment. On a domain-specific architecture, it's almost exactly the opposite situation. We can make alignment go blindingly fast with a special purpose dynamic programming engine, but filtration fundamentally is memory limited. We take these seeds and we look them up in a database, which is tens of gigabytes in size. And so that's necessarily in external DRAM, and you're limited by DRAM bandwidth and energy. So we retooled Darwin. We changed the algorithm to use a faster but leakier filtration algorithm. So we get a lot of false positives coming out of the filtration step. There are only a couple false positives coming out of GraphMap. But because we can do alignment so fast, it doesn't matter. We can run those false positives through the full dynamic programming. We get an enormously expensive edit, so we know that that was a bad alignment. We throw it away. If you just did this in software, it would be 2.1 times slower. But by then throwing our special purpose hardware for dynamic programming at it, we actually wind up 400 times faster, because our 150,000 times speed up on the dynamic programming part of the algorithm more than compensates for that larger number of false positives. We then make a number of optimizations to the memory system. We wind up with an overall 15,000 times speed up on the entire algorithm, considering all of the parts. I'll talk about some of those others to illustrate a few other examples of how domain-specific architectures get their performance. The next thing I want to point out is how memory dominates. One way it dominates is in power and area. If I look at a number of accelerators we've built, the GACT is the dynamic programming part of our genome accelerator, DSoft is the filtering part, and EIE is one of our deep learning accelerators. They're almost completely dominated in terms of both area and power by memory. And in fact, if you're comparing different possible ways of building an accelerator, a really good first cut at estimating is to ignore the compute and just compare the area and the power of the memory. And you'll actually get a pretty close estimate. It's a good way to winnow down design alternatives and explore the design space very quickly before you start trying to design the logic for some of the more promising candidates. A lot of this memory is actually not memory, it's communication. Reading from a local SRAM is only about 5 picojoules for a 32-bit word. Reading from a global on-chip SRAM is about an order of magnitude more. Now, it turns out this on-chip SRAM is actually built out of many small local SRAMs. And the difference in energy, that 45 picojoules, is the communication energy, getting your address to the bank you need to access, and then getting the data back from there. And going off-chip, even to LPDDR, which is about the least energetic, about the most efficient external DRAM you can get today, is another order of magnitude larger. So the key to getting efficiency is to get rid of the global memory accesses and to design your algorithms so you can get lots of small local memories accessed, such as with the traceback pointers in Darwin. Another example of this is in our most recent work on deep learning accelerators with Magnet. We use a hierarchy that uses DRAM, a global on-chip buffer, weight buffers, and then weight collectors to basically stage through many levels the weights and activations for deep learning. And this has let us hit record-breaking levels of teraops per watt for a deep learning accelerator. Now, as I said before, you have to tailor the algorithm to the hardware. In fact, designing a domain-specific accelerator is really an exercise in programming, but it's programming with hardware costs. where accessing global memory is super expensive and compute is super cheap. So you need to keep the memory footprint small so it can become a local memory footprint. An example of this is our GACT alignment algorithm. The core algorithm, as I said before, is Smith-Waterman. But if you're doing a long read alignment where the reads are about 10,000 bases each, and actually some of the newer long read sequencing machines, the reads are more like 100,000 bases each. But even back in the 10,000 base days, the dynamic programming matrix would have 10 million elements. And so the storage required to keep the entries for that matrix would be so large you could keep maybe one or two of them on a chip, and then you would run out of room. And we want to build 4,000 of these processing elements on a chip. So what we did is we developed a tiled version of the Smith-Waterman algorithm called GACT, which generates optimal results as long as the tiles overlap in a manner that contains this path. There's actually some recent theory that proves that. When we first did this work, it was an empirical result. The other way you can reduce memory operations is to break the memory abstraction a little bit. Back when RISC processors came out, viewing memory as just doing loads and stores was a very popular thing. You didn't want to have more complex operations. That was against the RISC mantra. But in fact, complex memory operations are a really good thing because they amortize that cost of communication of getting to the memory location over memory operations. And so, for example, with the filtration part of our Darwin accelerator, we have a distributed memory system that implements a hash table where we have to do roughly 10 operations, where we hash, we compute the address, we access that, we check for collisions, we increment with open coding if there is a collision until we find either a matching key or an empty location. Then we increment to bin, we check it against both zero, so we can increment a non-zero count, we check it against a threshold, so we can put the candidate out. And if we had to go back and forth across the memory system for each of these operations, it would be prohibitively expensive. If we had to rely on caching to avoid multiple traversals across the memory system, we would introduce numerous synchronization problems because many memory channels are simultaneously updating the same hash tables. It's much simpler to send a single message to the memory system and have the compute happen at the memory system. This is a technology we actually developed back at MIT in the late 80s and early 90s called message-driven processing. And it's extremely effective at amortizing communication costs by moving computation to a memory. Another thing that special purpose hardware does for you is it lowers the overhead to exploit sparsity and data compression. And these are wonderful techniques because they both multiply memory bandwidth capacity. And most algorithms wind up being memory limited at some point in time. And a great example of this is the EIE accelerator we built for deep learning, which stores a sparse matrix. We published a paper at NeurIPS in 2015 pointing out that neural networks can be sparsified. You can basically, depending on the network, throw away between 30% and 90% of the weights without losing any accuracy. When we sent this in to be reviewed, many of the reviewers complained, oh, this is irrelevant because everybody knows that the sparse matrix package is less efficient than the dense matrix package until your matrix is less than 1% dense. We argued back in the rebuttal, unfortunately they listened to us, that if we built an accelerator, we could make it efficient at 50% dense. And that's in fact what we did with the EIE. In fact, it's efficient at probably closer to 60 or 70% dense. We did this by having special purpose hardware to walk the sparse matrix structure using extremely compressed and efficient encoding of that structure. We also used scalar quantization to encode the weights. So we could have a 16-bit weight encoded as a codebook entry. So if you had 16 entries, it was a 4-bit symbol that looked up in the codebook. And again, if you tried to do that on a CPU, the overhead would be enormous. In special purpose hardware, it's almost free. Now, it turns out that if you had to build a different computing engine for each application or even each domain you wanted to accelerate, it would be extremely expensive. But when you look at what it really takes to build these computing engines, it's not the Smith-Waterman engine. Writing the RTL for that is a day's work at most, actually, maybe even less. It's basically those recurrence equations dropped into Verilog. And even the DSoft thing with the on-chip network and the distributed hash table, is a relatively easy thing to design. All of the effort is in the rest of the system. It's building a high bandwidth hierarchical memory system. It's building an on-chip network. It's building programmable control and operand delivery so you can tailor for different applications within the domain. And so it turns out that a GPU is really just an ideal platform to tack on domain-specific hardware. And that's not an accident. It's because GPUs were built from the very beginning to be platforms for domain-specific acceleration. Originally, the domain was raster graphics. More recently, we've extended that to ray-traced graphics with our RT cores. And then we extended it to being for deep learning with the tensor cores. And you can imagine tacking on a bioinformatics core, Smith-Waterman core, to make it work much better on bioinformatics algorithms or other things. I've played around with logical inference cores and SAT solving cores. And the reason that a lot of these cores work, and in fact that a GPU can essentially match the performance of an accelerator designed just for something like deep learning, is illustrated on this slide. And it's because fetching and decoding an instruction, like I showed of that slide with the ARM core, is very expensive. It turns out a GPU, because it's in order, non-speculative, has much lower overhead, but it still has a lot of overhead. Say if we normalize everything to a 45 nanometer process, about 30 picojoules to fetch and decode the instruction and fetch and store the operands. So if you do this for one operation, like a half precision floating multiply add, it dominates. And an accelerator could beat the GPU. But when we introduced the tensor cores in our Volta generation of GPUs, the FP16 tensor cores, the bulk, 80% of the energy is going into the payload, going into doing the 128 floating point operations, and relatively little is going into the overhead. So the most a dedicated accelerator could do over this is 20% better. And in Turing and Ampere, where we now have integer tensor cores, we close that gap to 12%. So there's almost no point in building an accelerator for just one application. You're much better off leveraging the design that's already there in the GPU for all these other things, and getting essentially no overhead. So as I said earlier, accelerator design is really programming. This is the way I would write the algorithm for the dynamic programming part of the genomics application. And what I'm doing here, this isn't a program that executes in time. It's a program that specifies what operations need to take place. These really should be for alls. There's no notion here of ordering. So I may even be doing the for all in a way that if you did it sequentially would violate dependency constraints. But what this really does is it generates the computation graph. And then separately, you need to say how to map that computation graph in time and space, where it says map Hij, that's the computation of Hij here, to a particular processor at a particular point in time. And that mapping can be checked to make sure that it obeys dependency constraints. You can compare different mappings in terms of their performance, their efficiency, their memory footprint. And you compare them based on hardware costs. A lot of what's wrong with the way people write algorithms today is they're based on this very obsolete notion of big O notation, where every operation is unit cost. Referencing memory is unit cost, doing an add is unit cost. Well, referencing memory, if it goes to global memory, is at least 3, maybe 4 orders of magnitude more expensive than doing that arithmetic operation. So that's a bad set of costs. People need to use hardware costs to optimize their algorithms. Well, I think I'm a little bit over time, so let me move on to the conclusion. Moore's law is over, but we really need to continue scaling performance per watt. A lot of productivity gains in the economy really depend on continued computing performance increases. Unfortunately, domain-specific accelerators can fill this role that used to be filled by improving process technology. With specialization and custom memories, we get efficiency. That efficiency lets us deploy thousands of accelerators in the place of a single CPU, which gives us speed up. We typically have to co-design our algorithms, but that's usually pretty easy to do. If you understand the fundamentals of the algorithm, you can break those sequential bottlenecks and the dependency on global memory that were designed as a convenience, because that was how to optimize them for legacy architectures. And GPUs really make an ideal accelerator platform because, quite frankly, they were designed to do that from the very beginning. They've got all the things that are hard to design, global and local memory, on-chip network, communication, and control. And designing the custom blocks that accelerated a particular domain of applications is actually a relatively easy thing to do. And designing those blocks, in fact, designing the accelerator as a whole, is really programming with a hardware cost model. And to me, a very exciting research area is building the tools that automate the mapping of those programs to hardware. And so I'll take any questions as long as time allows and show you this picture of where I actually am right now. I live right here on the lake in northern Nevada.
Thank you, Professor Daly. So we have a sequence of questions here for you, but in the interest of time, I'll make it fast for you to answer a few of them. So one of the questions I could see is that power is a huge challenge for the GPUs. What are your recommendations, to address them in an optimized way, so that we don't, lose out anything on the speed or the area, but we optimize the power to the best of it for the given technology.
Right. So what we try to do with the GPUs is two things. One of them, I probably should drop back to this slide, is we make them very simple to begin with. GPUs, both CPUs and GPUs get their performance from parallelism, but CPUs do it in a covert way. They actually execute a lot of instructions in parallel. A modern CPU will have 8 decoders and be able to launch 8 instructions simultaneously. And then they'll try to put everything back into sequential order, and that's extremely high overhead. That's why even that simple ARM-A15 core was 250 picojoules per instruction. A GPU is about an order of magnitude less than that. And the next thing we do is we try to, for critical applications, build domain-specific accelerators that amortize that overhead. So for example, for deep learning, the tensor cores amortize that overhead so that almost all the energy is going into the primitive arithmetic operations, which gets me back to this slide. So if you understand the cost of things, if you're not a Lisp programmer who knows the value of everything and the cost of nothing, but if you do understand the cost of things, you then design your algorithm to compute in the lowest cost way that can then be mapped into one of these accelerators on the GPU, and that gives you the best efficiency.
Thank you. So there's one more last question. You mentioned at the beginning of your talk that faster computing, better algorithms, and more data. What do you see any other dimensions, getting into this sequence, which provides more value?
Well, I think, in the computing world, this kind of sums it up. And, these 3 things all have many aspects to them. So faster computing, one aspect is building better core GPUs. Another aspect is building better accelerators that connect onto them. Yet another aspect is building better networking that connects them together in a data center. The better algorithms include, fundamental algorithms, as well as better neural network models, better optimization techniques for neural networks. There are many aspects to each of these. And of course, since most of our computing these days is very data-driven, more data tends to enable better algorithms. If you have a larger neural network model, you need more data or you'll overfit a limited data set. And so they go hand in hand.
Thanks, Professor Daly. I still see some questions on the stage by Professor Vijay and Dr. Satya. In the interest of time, we'll move forward. I would like to take this opportunity to thank you on behalf of the conference organizing team and on behalf of VLSI Society of India to sparing up time from your busy schedule. We really appreciate your time and valuable insight provided by you. So kindly accept this virtual token of appreciation from our side. We'll be shipping a physical token of appreciation to you post the conference. Thank you so much.
Thank you very much. I'm honored you asked me to participate. Have a great day.
Thank you, sir. Okay, so with this overview talk by Professor Worley, we'll move forward in our agenda. So next in line, we have our visionary speaker, Paul Cunningham. He's Corporate Vice President and General Manager for Systems Verification Group at Keynotes Design Systems. Paul's responsibility includes system verification, which further is subdivided into logic simulation, emulation, prototyping, formal, VIP, and debug. Prior to this, he was responsible for Cadence front-end digital design tools, including logic synthesis, design for test. Paul joined Cadence in 2011 as a part of acquisition of Azuro, a startup developing concurrent physical optimization and useful skew clock for tree synthesis, where he was co-founder and CEO. Paul holds master's degree and PhD in computer science from University of Cambridge, UK. So with this, I have a little surprise in place for you guys. So I would request Paul to come on stage. Over to you, Paul.
Good morning, good afternoon, good evening, depending on wherever in the world you're participating in this conference from. I've been associated with the VLSI conferences right since its inception, but this year it is different. It is the first virtual VLSI Design and Embedded Systems conference, and Cadence is delighted to be a Silicon sponsor for this year's conference. For this specific keynote, we're going to do it a little bit differently. I'm going to start off by sharing some high-level industry trends, and then I'm going to hand it over to Paul Cunningham, who is the general manager of our systems and verification group, who's going to talk to trends in the cyber physical systems domain and talk about how Cadence is addressing those challenges. So let's get started. Once in every generation, there is a disruptive technology that redefines the industry landscape. In the last decade, that was mobile computing. It is absolutely unprecedented that today we are seeing 5 such disruptive generational trends. These are 5G, hyperscale computing, artificial intelligence and machine learning, autonomous vehicles, and industrial IoT. And they're all anchored around generating and processing large quantities of data. And they're all enabled by computational software. So in reality, it's computational software that's driving the future of the technology landscape. If you look at the data, the very large quantities of data that's being generated, that needs to be transmitted, it needs to be stored, it needs to be processed, and it needs to be analyzed. And this indeed is driving a tremendous silicon renaissance. If you look at some of the specifics here, 90% of the data that exists today was generated just in the last 2 years. 80% of that data is unstructured, which means the conventional ways of analyzing the data break down. And that's the reason why only 2% of this data is being analyzed today, which means only 2% of the data is being meaningfully used. If you project this into the future, industry sources say that over the next 5 years, the rate at which data is going to be generated is going to continue to grow at about an 81% compound annual growth rate. And the largest drivers of this new data are going to be video and augmented reality and virtual reality applications, which means it'll continue to be unstructured data. Now, if you look at this big data revolution that's going on around us, it presents many challenges. I mean, dealing with big data. First of all, we have to use artificial intelligence and machine learning techniques to analyze and make sense of the data to be able to use it effectively. For that, we need to first and foremost tag the data for training purposes, which is a manual and error-prone process. And then, of course, we need to build the right analytics flow, which again is manual and labor-intensive. Now, if you look at the data journey from the endpoint where the data is generated all the way through the data center in the cloud, and if you look at the latency at various stages, it's very clear that depending on the end application, the processing of the data needs to happen at different points in this stack. Specifically, if you're looking at real-time applications, then it requires very low latency, which means the processing needs to happen closer to the endpoint or at the edge. Now, all of this is driving tremendous innovation and investment in storage technology, in processor architectures, and in transmission technology for the data. The other thing that's very important through this value chain is security. Security from the endpoint through the edge and to the cloud data center. And the industry is aligning and coming together to provide a solution for security across the hardware and the software stack. If you look at some of the recent M&A announcements, it's obvious that they're all chasing the opportunities presented by this drive in hyperscale computing. And if we, again, look forward, we find that this is going to be the driver that redefines the industry structure and makes many more applications possible, many more solutions possible across various industry verticals. Much like mobile was the key driver for redefining the industry landscape in the last decade, it's going to be hyperscale computing that's going to be the key driver for redefining the industry landscape and defining new applications and solutions across many different verticals in the coming decade. With that, over to Paul.
Good morning, good afternoon, good evening. It's an honor and a privilege to have this opportunity to be with you all here at this 2021 Virtual VLSI Design and Embedded Systems Conference. Thank you for taking the time out of your busy schedules to listen to my presentation. The theme of this year's conference is from the transistor to cyber-physical systems for solving societal challenges. What a wonderful theme for a conference and for our community. The world around us is changing so fast. I recall a moment maybe 10 years ago when my first son, then 4 years old, walked up to our TV on the wall and started trying to touch the screen to interact with it like it was an iPad. Fast forward to today, and Alexa is basically a third parent in our house. My kids ask her what questions about their homework, ask her to remind them to do things, and to call their phones when they can't remember where they've left them. Our future is absolutely one of intelligent connected devices that see, hear, touch, and even smell. Cars that drive themselves. Homes and offices that intelligently control climate and lighting. And of course, with this cyber-physical revolution comes an explosion of new semiconductor design. From the data center to the edge, to a smart grid in our homes, offices, and factories, to medical devices, cars, planes, industrial equipment, process control systems, and robotics. Everything that happens in this cyber-physical revolution relies on semiconductors. Analog, digital, mixed signal, chip to package to board. A continuous blurring of the lines between hardware and software. So how does this cyber-physical revolution relate to the EDA industry? The key thing we're seeing at Cadence when we talk to our customers is a shift in mindset. Our customers are no longer just looking for a partner to automate their design. They're looking for a partner to help differentiate their products. It's not just about automation, it's about automation with the best performance. And their challenges are not only at the chip level. It's performance of the overall system that the chip goes in, and performance of the end applications built on these systems. And these systems are no longer static systems. They're intelligent learning systems that are continuously evolving and customizing their user experiences. At Cadence, we feel perfectly positioned to respond to our evolving customer needs. If you step back from our products themselves and ask the question, what makes the people at Cadence so special, so unique? You come to the conclusion that what Cadence has built over the last 30 years is one of the world's best computational software teams. We have more than $2.5 billion in revenue and spend 40% of this on R&D engineers who know how to write very complex computational software. We have many of the world's experts in numerical solvers, SAT solvers, SMT solvers, graph algorithms, computational geometry, and so on. At Cadence, we are taking our core competency in computational software and using it to create new products and new value at the system level. We're also taking this same expertise and using it to make our own solutions intelligent and intuitive. We call this our intelligent system design strategy. And I feel it's a perfect strategy to help fuel and enable the cyber-physical transformation that is going on around us. A perfect example of us leveraging our strength in computational software to grow from design performance to system performance are our Celsius and Clarity system analysis tools, which we launched last year. These tools are entirely homegrown at Cadence and build on our deep computational software expertise in advanced, massively parallelized matrix solvers in the SPICE and power sign-off markets. With Celsius and Clarity, we leverage this expertise to enter the system analysis market of finite element solvers and fluid dynamics. Celsius and Clarity are disrupting this market with solutions that are just 10x faster and much more scalable than existing products. And our journey here is still just beginning. Our original Clarity launch last year was with a frequency domain-based solver. This solver has the best accuracy and we can scale it way beyond any other tools in the market. For example, we can run an electromagnetic simulation of an entire DDR DIMM. Now, more recently, just last quarter, we extended Clarity to include a time domain-based solver. While not as accurate, this solver has almost unlimited scalability with a distributed architecture that is cloud-enabled. It can be used to simulate a whole car or airplane. Putting these two solvers together in one unified solution is a truly amazing technical algorithmic achievement. And most recently, just last month, we announced an agreement to acquire NUMECA, accelerating our ramp into computational fluid dynamics. Another key thing we've been able to do by building Celsius and Clarity from the ground up at Cadence is to integrate them tightly with our design tools to offer a truly unified solution for both design and system 3D IC performance. Here we've connected together tools across all of Cadence, from PCB to IC to interposer to interconnect, to allow concurrent implementation of a 3D IC across multiple teams, but while also enabling continuous system-level analysis of either individual dies or the whole 3D IC package for power integrity, electromagnetic, or thermal. It's a beautiful solution and something Cadence is uniquely privileged to offer as part of our intelligent system design strategy. Another great example of our intelligent system design strategy at work is our Palladium and Protium dynamic duo. Cadence has been a market leader in emulation for more than a decade with our flagship Palladium emulation system. Palladium uses a custom proprietary processor we design and tape out here at Cadence. It's the ultimate chip debug accelerator, offering lightning-fast, predictable compiles and the ability to stop, start, and probe any signal at any time. But now, Palladium has a system-level partner, Protium. Protium is targeted at accelerating pre-silicon embedded software debug. Protium runs 3 to 5 times faster than Palladium, but like Palladium, it also comes in a standard data center rack scalable to multi-billion gate designs. We've also designed Proteum from the ground up with a unified compile flow and unified transactors and hardware connectors to make it very, very easy to move a design from Palladium to Proteum as your chip stabilizes and the focus moves from chip debug towards software debug. Where Palladium is our customer's ultimate debug machine, Proteum is their ultimate performance machine. And they can buy whatever mix of each achieves the highest verification throughput for their specific product and end market needs. A final example of Cadence's move from design excellence to system-level innovation is our Tensilica configurable processor and DSP design IP. Here we're fusing our deep expertise in computational algorithms with a world-class configurable extensor processor architecture to offer a comprehensive family of system-level compute solutions. If there is one element of our Cadence solution today that is most spearheading our commitment to a cyber-physical future, then it is Tensilica. This unique technology can enable audio, radar, LiDAR, vision, all with a common configurable architecture and all with industry-leading performance per watt. Okay, now let's move from system innovation to pervasive intelligence. Just like machine learning is central to the cyber-physical revolution, machine learning also absolutely has the potential to transform almost all our products at Cadence. We're now able to take designer intuition and encapsulate it in an algorithm. A first great example of this is in our Innovus place and route system. Here, despite decades of investment in deductive algorithms to pick the best logic placement, best signal routing, best clock tree topologies, and so on, the harsh reality is that our customers still perform many, many trials of place and route with different settings, scripts, knobs, and so on, to achieve the best overall power, performance, and area, or PPA, as we call it. By putting machine learning into Innovus, we're able to begin to automate this iterative manual process and drive significant improvements in PPA without any human needing to be in the loop. And honestly, without any direct deductive understanding of place and route in and of itself. It's a abstracted black box optimization through intuitive machine learning and neural network training. It's amazing, really. And our journey here is just beginning, but the early results, as you can see, are already very impressive. Another example of machine learning at Cadence is our new Excellium ML solution. Now, a significant fraction of our customers' digital logic simulation workloads are with pseudo-randomized test benches, for example, with a UVM environment. These tests are typically grouped into banks of thousands or even tens of thousands of tests, all of them firing pseudo-random stimulus to try to catch corner case bugs. It's an extremely compute-hungry task, but also not a very efficient one. Much of the compute resources consumed by this randomized stimulus, injecting values into the design that cover points already covered by previous randomized stimulus. Essentially, it's just covering what has already been covered before, time after time after time, with only a very infrequent increase in the actual coverage to find new parts of the design or functional specification. What we've done with Excellium ML is to build an AI system that can learn from the last time the tests were run and guide the randomization kernel inside our logic simulator Excellium to be smarter. I say to load the dice, as it were, to roll a 6 more often and hit the required coverage points with dramatically less compute resource. Again, as you can see, it's early days for us, but this technology is showing very compelling results and has very, very strong traction amongst our customer base. So, before I wrap up, I really wanted to acknowledge that intelligent system design, and indeed a cyber-physical future for all of us, cannot be realized by Cadence or any one company alone. The most important thing of all is our ecosystem, how we work together, industry with academia, hardware and software challenges, system versus chip versus fab, packaging, design automation. Only together can we do great things and shape the future. So, thank you all for your time today. It has been a privilege to have the chance to talk with you about Cadence and our intelligent system design vision, and how this vision is, in our view, a key enabler and a key contributor to the ecosystem to deliver a cyber-physical future for us all, with real societal changes for the better and for the greater good of the world. Please take care, stay safe, and stay healthy.
Thank you. Thanks, Paul and Jaswinder, for the insightful talk here. And as I said, we had a surprise for you, and hope you guys make out. So we had a surprise entry of Jaswinder Singh Hoja, who was our ex-vice president, ex-president of VLSI Society of India, who started the talk, and Paul joining in. So Paul, we have again, a huge queue of questions. So the most prominent one I found is, and this comes from one of the students, that you being a leader of a computation software company, and for which you do softwares for a lot of cyber physical applications, namely like autonomous, to optics, intelligent manufacturing, etc., etc. So which one is the toughest challenging application you saw where the software got a hard time to get it done? So this comes from a final year engineering graduate student. So I would like to see hear your insights on it.
Yeah, that's a wonderful question. I mean, I don't know if I can call out one challenge as the most complex for us all. I mean, this combination, this kind of creation of a sensing, intelligent, adaptive world, I think that's impacting all markets, all verticals. But I would cut maybe a little bit horizontally there and say that I do think the idea of intelligent computing, whichever industry it's in, so AI essentially, that we are in an era now, honestly, of probabilistic compute. We went from kind of geometry to calculus, right? And now we're into really embracing intuition in an algorithmic sense. And I think that is challenging all of us in all markets in so many different ways. But it's wondrous. I mean, it is, and it will continue to transform the world. And so I'd kind of call that out.
Thank you. Thanks, Paul, for your insightful discussion and answering this query. So in the interest of time, we'll move further. We thank you, Paul, for your valuable time here. Kindly accept our virtual token of appreciation from the conference and the VLSI Society of India.
Thank you.
Thanks. Thanks, admin, for the virtual applause as well. Thank you, Paul. Appreciate it. So now it's time to move to one of the most exciting part of today's inaugural session. We have our honorary distinguished visionary speaker, Dr. V.K. Saraswat, honorable member of Niti Aayog, along with us, already joined on the stage. Though he don't need any introduction, but let me take this opportunity to briefly introduce him. So Dr. Vijay Kumar Saraswat is India's most gifted scientist and an accomplished researcher with more than 4 decades of experience, spanning over several fields and areas in both basic and applied science and defense research. Apart from being a scientist, he's a rare combination of an innovator, technologist, and visionary. Born at Gwalior on 25th of May 1949. My pardon for misspelling. 24th happens to be my birthday. So 25th May 1949, Dr. Saraswat completed his engineering from Gwalior, Masters of Engineering from IISc Bangalore, and followed by PhD from Osmania University. During his career, from scientist to scientist advisor to defense minister, director to director general of DRDO, and secretary to Department of Defense and R&D, Dr. Saraswat has been credited with development of liquefied petroleum rocket engine and missiles, namely Prithvi, Dhanush, Prahar, indigenously. He is the principal architect of the ballistic missile defense program of India. Dr. Saraswat is recipient of multiple distinguished national and international awards, including Padma Bhushan in 2013, Padma Shri in 1998, and Vikram Sarabhai Memorial Award from Indian Science Congress in 2011. The list is huge of his own accomplishments and the awards. Dr. Saraswat is fellow and member of multiple professional bodies. His honorary cause was conferred upon him by more than 18 universities across globe. He has authored and presented several papers in national and international conferences. He has guided multiple students on PhDs. Dr. Saraswat presently is a member of Niti Aayog and shouldering many honorary positions in Government of India in research and academic institutions. With this, we are really honored to have you here, sir. I would pass on the stage to you to kindly start your vision and your talk about very large-scale integration design trends and drivers. Over to you, sir.
Good morning, namaskar. I hope you can all hear me. And a very interesting lecture from Paul Cunningham. I just happened to listen to part of it, and I was really enchanted by the kind of progress that is being made in the simulation and the design of systems using the current technologies which are emerging today. I would like to share with you my experience and what is happening in our country with respect to the VLSI design. I have a small presentation I would like to share with you. Let me see if I can make it happen. Yeah, I think I succeeded. So that's a big achievement today. Yeah, so I'm no expert in VLSI, nor I am an expert in designing of VLI systems and all that. Whatever I'm going to talk to you is based upon my few years of experience as a user and also my association with large number of designers in the country, particularly during the National Supercomputing Mission program and also India's microprocessor program. I have interacted with large number of scientists and academicians who are actively involved in the VLSI design, and based on their responses and my experience with them, I'm going to share with you certain aspects of VLSI design trends and where India is going into. So if you look at VLSI in its totality today, starting from the early days of 1965 when the first transistors coming in 1948, when Gordon Moore predicted that transistors would continue to shrink, and he said that doubled transistor density every 18 to 24 months, doubled performance almost about again 18 to 24 months, and history has certainly proven him right. And that's why he keeps laughing all the time. But what we see today, by year 2020, we have seen 5 nanometer reality. Physical limitations are still there, economic limitations are there. Do you think that with the kind of processors which I used when I was designing the Prithvi missile 8086, 80286, 80386 as my early embedded system design process, to what we have done in the ballistic missile defense programs when we went to power PCs and things like that. So with few transistors at that point in time to billions of transistors, what is happening in the form of scaling today is the direction in which the entire VLSI program across the globe has moved. And number of applications that have emerged, right from the CMOS technology to low power VLSI, signal processing, noise reduction, wireless communication, image processing, finite state machines, encryption, finite and variety of ALU units and FinFET modeling. The whole spectrum is very, very wide. And today, with the onset of cyber physical systems, with the onset of Internet of Things, Internet of Everything, I think this particular field is becoming more and more demanding. In that respect, the trends in the VLSI research are multiplying in terms of the applications, particularly starting from microprocessors. Then we had our DSPs, then for the video, for the wireless, handsets, smart cards, sensor networks, RFID systems, and now we have seen in the last pandemic the tremendous use of medical devices, and design challenges are also multiplying in terms of area, in terms of performance, in terms of complexity, and the test and the yield and the power, reducing the power as much as possible, providing a huge flexibility, and also multiplying different functionalities, and also maintaining the reliability both in terms of the process, voltage, constancy, and temperature. And one thing which is emerging today, and particularly in India, we have realized with the major digitalization program which is going across all the states, districts, and all that under the leadership of our Honored Prime Minister, we find that secrecy and privacy is becoming a very, very important aspect. And that will certainly put in much more burden today as far as the designers are concerned. There are three key drivers which have seen happening from the early 60s when the mainframe systems were enforced with a few million units, maybe 1 million units at that time. Then 1980s, we saw the mini computers with the integration was continuously increasing. In the 90s, we had the PCs with 100 million units. And by 2000, we have desktops and internets with about 1 billion plus units and users. And now we have mobile internet, which is really expanding in its totality. So what we see that iPads, smartphones, Kindle, tablet, cell phones, car electronics, GPS, ABS, virtual realities, mobile videos, home entertainment. I think the functionalities have improved, the mobility has improved drastically, and the sizes have come down in a big way. That is the computing growth drivers from 1960 to 2020, and it is certainly going on and on and on. Then you see the kind of design challenges, some of them have been overcome, some of them still remain and continue to be bugging the designers today. You have the requirement of ultra high speeds, the power dissipation and supply is a major issue. The growing importance of the interconnect. I think this is one area which all the designers have been now focusing to improve the performance of the interconnects and reducing the noise and the cross talk, and of course reliability. And finally, we may go for 1 nanometer or 5 nanometers, but then the manufacturability becomes always a major issue, and clock distribution. In terms of the macroscopic issues which are related to the market, which are related to the economics, one is basically time to market. And I find that this time is coming down drastically over a period of so many years. Then, of course, the design complexity is continuously increasing because now we are dealing with millions of gates. High level of abstractions are coming, reuse and IP was being discussed in the earlier lecture also. Then you have system on chip and interoperability. The design approaches, of course, also keeps changing, but today we have the two approaches. What is top-down approach and the bottom-up approach. Top-down approach is with respect to the top block, identifying the sub-blocks needed to build the top-level block and divide further up to the leaf levels. And bottom-up approach, where identify the available building blocks, choose them to build the bigger cells, and use them to build top-level block. So this is what India has been following. Mostly we are looking at the bottom-up approach, and many people do the combination thereof. So You have right from the device to circuit to the gate to the module and then the realization of the systems. Most of you are aware of this particular slide. I won't spend much time on this. The VLSI design processes, the specifications going into functional design and logic design, circuit design, physical design, and testing and fabrication. And I minded the entire process is even today iterative in big way. So you carry on various aspects, but with a certain amount of iteration till you come to the physical design, where you focus on partitioning, you focus on floor planning and routing. These are some of the processes we have. And then we have methodologies. You can see in one chip, you have memory, you have custom macro, you have number of gates. So full custom design, semi-custom design, gate array design, standard cell designs, CPLD based designs, hardwired control, PLA based control, and HDL based methodology, RT level synthesis, IP codes, SOCs, TSPs, MEMS, in the entire gamut of things. In fact, when we were doing MEMS in our country, we realized that because we did not have the kind of stability in the silicon device manufacturing in the country, even though the academic institutions were able to come out with some kind of simulated designs and so on, the ultimate realization of a sensor or a device was still a problem. So I think the experience of silicon in terms of transistors and all that getting translated into MEMS was very important, and that has been realized in our country. This is the typical fabrication cycle where you start with a photoresist silicon oxide layer, then you have prepared silicon wafer, then you project light on the mask, and you get a patterns are projected repeatedly into wafer, then exposed photoresist is removed, and from there you go into areas unprotected by the photoresist are etched by gases, and then you come to the doping process where ions shower the etched area, doping them. Then of course you have the metal connector in which you have similar cycle is repeated to lay down metal links, new photoresist is spun on wafer, and step 2 to 4 are repeated. So this is a very complex cycle which many foundries have been following from time to time. In India, we have, of course, one foundry where this similar process is being followed at about 180 nanometers. But I think the expertise which is essential in all these processes is a real issue. We need to really make sure that this expertise is done, the skills are created, and only then you will be able to get the kind of maximum what we call as the expertise and the efficiency and the performance. In terms of simulation and the design characteristics, as Mr. Paul was mentioning, the key CAD capabilities and increase the challenges to sustain such an exponential growth to achieve giga-scale integration have shifted in a large degree from the process of manufacturing technology to the design technology. I just discussed with you the manufacturing technology, but the design technology where you started with 0.062 megahertz, 6 micrometers kind of a SPICE simulation. Then you went over to CAE system, silicon compilation. And then you had HDL synthesis. Then you have top-down design emulations. And then we have cycle-based simulation, formal verification. So these CAD capabilities have happened in a big way. And what was being talked by Mr. Paul was very important because machine learning is what is going to make all the difference in all these activities in a big way. When you design more and more complex systems with kind of database which is being generated today during different processes of design, I think it will go a long way in improving this whole process of design simulation. The major drivers, they still remain the same. We have still an issue with respect to less power consumption. We would certainly like to keep on reducing. We have come to say 0.3 volts and things like that. But then price, more economic. So that's why the size of the wafer keeps on increasing to get more and more per wafer and things like that. More economical, more or less components per board, per system, less price, more economic, again high reliability, improved interconnects, more compactness, high speed of operation, less manufacturing costs, and area utilization and compactness. These are the challenges and the drivers. They are still remaining the same, but only at a level that once we were doing only 10,000 transistors, now we are doing 10 billion transistors. So that is the kind of complexity which is increasing, and that's where the interconnects also are becoming a major issue. Now, one of the things which is reaching a particular stage is the scaling, the technology scaling, which is important. From 10 micron technology to today's 28, 32, and even 14 nanometer technologies. At 10 micron, we are about 50 to 70 gates per square millimeter. At 28 nanometer, we have about million gates per square millimeter. And then in 10 micron chip complexity, we have only few thousand transistors. Today, billions of transistors. And you can see the two typical processors which are identified with multiple cores and threads, and the kind of numbers which in terms of clock frequencies and in terms of power consumption and in terms of packaging have been realized. And just compare with this with the first integrated circuit in germanium built by Jack Kilby at Texas, and where here only 5 components like transistors, resistors, and capacitors, to what we have come in terms of multiplication of large number of systems. According to the International Technology Roadmap for Semiconductor IRTS projection, the number of transistors per chip and the local clock frequencies for high performance microprocessors will continue to grow exponentially in the next 10 years too. That means what we are seeing in 2020 coming to something like 180 nanometers, or maybe now coming down to 5 nanometers. Coming to the transition region, expectation is by the time the quantum devices and the atomic dimensions will come by 2040. So this is a trend in future which has been predicted by this international body. And the general trend that we expect in the next 10 years, according to this body, is increasing of transistor count for microprocessors and DRAM memory elements, shrinking of line widths of the ICs, and growing chip die sizes and increasing semiconductor fabrication process complexity. This is a generic statement, and we are seeing it happening today. Another area is the technology scaling. Along with that is the frequency scaling. The main twofold frequency improvement for each technology generation is primarily due to the factors like the reduced number of gates employed in a clock period, what makes the design more pipeline, and advanced circuit design techniques that reduce the average gate delay beyond 30% per generation. That is the kind of frequency scaling we have been able to look at. And our aim for going for low power design in terms of algorithms, architectures, and circuits has received significant attention and research input over the last decade. For example, if you take process device, you have threshold reduction, multi-threshold. You take circuit level, you have transistor sizing, you have logical optimization, then you have activity-driven power down, then low swing logic, adiabatic switching. All these features are coming at the circuit level. At the architecture level, of course, you do voltage scaling, then parallelism, instruction set, and signal correlation. At algorithm level, we have complexity, concurrency, locality, regularity, data representation. And at system level, you go on the design partitioning. In fact, this is one area which many times we have been struggling, the design partitioning and reducing the power thereof. All of them have made a very, very high impact as far as the VLSI systems are concerned. So there is a prediction which has been made, while the earlier slide also gave a similar impression. The same thing has been highlighted here over, where you can see that from 180 nanometers in 2018, we come down to 10 nanometers, then 7 nanometers, and then atomic dimensions. So the era of easy scaling is over. We are now in a period where technology and device innovations are required. Beyond 2020, new currently unknown inventions will be required. It will not be the same. For example, 13% decrease in feature size every year and now become 10%. Era of simple scaling, 60% increase in complexity each year. Now 6.3 years for microprocessors and about 12% for the DRAM. That is the kind of evolution which is taking place. This is, of course, the same thing identified what is going to happen till 2030. We have size 0.01 nanometers. Here you reach down to 5 nanometers, and then NWS and NTs. Evolutionary CMOS will be the order of the day. Now, IC manufacturers from the various manufacturing companies who have done work from 2012 to 13 to about 18, 19, if you see the data, you will find that we have reached what is called 8 to 7 nanometer nodes in terms of variety of features like memory, 0.01 micrometer and square, SRAM, device planar, FinFET, and channel SI, voltage about 0.8 volts, and 0.8 volt coming down to 0.5, 0.5, and then ultimately we have come to the about 0.3. And similarly, in the case of memory, you are coming down to from 32 nodes to as low as about 16 to 14 nanometer nodes. And similarly, in the flash, you have a tremendous improvement in terms of density greater than 1 trillion with 3D chip stacking and 3D BICS and X-point PRAM and so on. So embedded memory SRAM bit cell is expected to barely scale, and end product cost might go up even for the same SoC complexity. That is the kind of company's prediction is there as far as these devices are concerned. And there is a similar indication which has been given by the IMEC research, where they have indicated that the memories right from one is the access time. As initially when we were working at 10 megabytes, 100 megabytes, and STT, RAMs, and so on, you will have 1 nanosecond kind of access time. But as you are going to 100 GB, 1 terabyte density per die, you find that your access time is increasing. And even whether you are on a 3D RAM or 3D SCM or 3D FinFET, all of them are going to give you higher density per die, but then you have an issue with respect to the access time. So these are the kind of predictions which are being made through the research of IMEC, which is being cataloged here. So when long-term multi-decade device roadmap exists, as we have seen, base CMOS geometric scaling has saturated. So you have DRAMs, you have FinFET 3D, you have gate all around, you have photonics coming in now, you have PCM SCM, you have FPGA 2.0. Then of course, by 2022, you are also getting carbon nanotubes and 1 nanometer transistors, and ultimately beyond that will be neuromorphic computing, and we are all working now on the quantum computing systems. The quantum computing is a major program which Government of India has also initiated recently, wherein multiple pathways are being pursued. So probably if the quantum computing becomes a reality, a lot of questions worldwide have been raised as far as its commercialization is concerned. But I'm sure, like we solve the problems in the case of silicon, I think we will solve the quantum computing problem also. And at that point in time, what happens to CMOS, we'll have to look at it in a serious manner. So cost of transistor increasing, economies of technology scaling, increasing process of, you can see here, continuously changing device geometries, and the cost increasing on a pure scaling strategy. So increasing process flow complexity, longer flow, more fab space, more requirements, equipments, increasing equipment and materials, these are all realities, increasing cost of transition resulting in reduced dollars per gigabytes, reduction driving lower investment return for planar scaling even when scaling is enabled from fundamental technology perspective. And diversified product needs from customer lead to complex fab mixes. So all the, in fact, the other day only we had a dialogue with the TSMC people, and when we were talking about setting up a similar fab in India, we found that the complexity which they were talking is not what we discussed about 5 years back. I think the complexity of the fab is completely changing in the today's scenario. Now, what is more than Moore? We find that there is a significant integration of functional diversification, which is taking place as far as the more than Moore is concerned. You will find that on the x-axis you see analog RF, high voltage power, passive devices, sensors and actuators and biochips all coming, interacting with people and environment, non-digital content system in package. That is what is happening. And whereas on the scaling side, you have already seen coming down from 130 nanometers to less than 22 nanometers and so on. So that's all beyond CMOS. So information processing, digital content system on chip is the order of the day. That is what beyond Moore is taking place. And if you look at the performance driven changes and the application driven changes, you will find from the planar CMOS material memory, the next 2010 to 20, we have seen 3D devices and 3D chip stacking, design tech optimization, particularly for applications like mobile computing, wearable computing, everything, everywhere connectivity and so on. And we are also seeing that when we go to next generation, you will see nanosheets devices, CNTs, 3D multi-chip stacking and photonics. And that will be the part of our cognitive computing. And IoT certainly will draw the same thing. And tomorrow when we go further from neuromorphic and computing to the quantum computing kind of applications. So this is the kind of projection beyond 2020 is talked of. There is a thinking that why 3D VLSI? Cost effective, low power, system on chip. Economy is a Moore's law, not scaling anymore. Growing gap between transistor and wire performances. You have mobile computation, communication, integration of disparate technologies. We are seeing now Bluetooth, this, that, everything is coming together. Emerging variants of mobile technology like Internet of Things, everything, and IoT, wireless, health, etc. So 3D VLSI can provide single chip solutions suited for the emerging market, both in terms of memory storage, communication, computation, and so on. So this is the whole process. We are stacking in 3D integration more. We are able to do integration more functionalities on a single chip. Heterogeneous functions and process nodes can be realized. Where optimum technology node selection per functionality can be achieved. Shorter on-chip communication wires like significant power performance improvement. And of course, it certainly has an impact on cost in terms of lower cost, less metal layers, better silicon utilization, optimal technology mix and match, and lower package cost. So you can have digital plus RF, analog plus memory plus sensors, integrate technologies with conflicted requirements. That is what the gain of the 3D VLSI program. And this is what has happened, 2D to 3D. In 2D, we had multiple chips on the PCB, and came system on a chip. We could do voice, camera, and the vision and storage. But now 3D packaging gives you 3D transistors like FinFET, GA, NWT, 3D stacking in terms of monolithic MEMS, devices, 3D packaging in terms of WOW and WLP, better performance, better power, better form factor. And then, of course, all this in the 3D package form, when it goes into the system integration, you get tremendous improvement as far as system performance and the bandwidth is concerned. Application specificity, both in terms of health, education, automobiles, everything, and process technology design solutions can be achieved by this kind of integration, both in terms of mobile, high performance computing, automotive, and so on. So future device possibilities through heterogeneous technology integration. This is what we are talking of silicon, but I think we are seeing now heterogeneous technologies which are getting integrated, like the 3D low power CMOS, integrated specialty technologies, and 3D IC technologies. All of them put together can certainly make a tremendous difference as far as the performance is concerned, because you have RF systems, you have analog systems, you have mixed signal systems, you have high voltage systems. All of them put together can meet multiple requirements as they are growing, and particularly now with this e-mobility coming, and the e-mobility demanding different kind of power devices, and also demanding silicon devices for the internal automobile and applications. I think the heterogeneous technology integration is going to play a major role. So new trends, as we are seeing today in VLSI design, are increased interconnect delay, scaling at the same pace as the device, increasing interconnect area up to about 40% of the area devoted to the interconnect, increasing number of metal layers up to about 5 layers for microprocessors, increasing planning requirements like physical design early on in the design cycle, and automated synthesis of logic and high level. So these are the new trends in the VLSI design. And this is just kind of a conclusion that we are seeing more flattening taking place, both in terms of power, we are seeing in terms of clock frequency, we are seeing in terms of thread performance, and we are seeing the same thing in terms of number of transistors. So this flattening beyond 2020 is the visibility what we are seeing today. Now, unless something drastically happens with respect to the technology, I think we will have to live with this flattening profile which is emerging as far as VLSIs are concerned. And that's why the international picture which has been given is the feature size 8.4 nanometer in 2021. The gate nanometers about 5 nanometers, voltage about 0.65, billions of transistors per die of about 24.7, wiring levels almost about 15, and maximum power about 198 watts. DRAM capacity is about 32 gigabytes, and flash capacity is about 256 gigabytes. Now, applications I would like to share with you what is happening in the sector of automotive, electrification drive, semiconductor demand. Developing differentiated electronics requires creation of specific solutions. Use of third-party IP accelerates time to market and increase design quality and reliability. And you can see, of course, the smaller letters you may not be able to see, but basically it is trying to indicate that you have multiple sensors. I think this slide gives you this. The multiple sensors which are going on into an automobile runs into trillion sensor vision. For example, ATC, magazine preventive maintenance, motor load and torque control, axis automated rotation adjustment, servo data from motor drives, power monitoring like power consumption, voltage and current, remote monitoring like alarm signal, operator monitor, sensing the data from various sources, automatic servo tuning, then machine leveling, load cell data which is required. Then you have distortion compensation with respect to vibration data and temperature data. So there's a huge number of applications like hydraulics, oil cooler, coolant. All of them are being monitored today in today's smart automobile system. That means the integration of trillion of sensors, which requires again a variety of things that to happen. In addition to the monitoring of that system, there's an infotainment which is getting integrated, and also the cloud connectivity which is required while it is moving. So you have body comfort, you have chassis safety, you have infotainment, you have powertrain systems, and you have cameras and secure cloud access, and ultimately the cloud, which is the data services reporting and tracking, which is important. So and security. So you have all kinds of interconnects like the Ethernets. You have USB, you have floating point and data path, audio systems. So that is the kind of complexity which is demanded. So automotive processors, which is what I'm presenting here, is probably 5-year-old kind of a thing, where you have clock speeds up to 1 gigahertz, low power consumption, configurable and user customizable, sensor, powertrain driven, all of them, in-vehicle infotainment and so on, process for under the hood and IVI application. So this is what the automatic system, but I think even in this area, the speeds and the frequencies have been going up. Another major area for the VLSI is emerging as the chemical sensors, and they are domestic sectors like the combustibles, the smart diaper, cooking aid and so on, like the medical sector for diagnostics, the compliance, patient monitoring, like the automotive industrial sector I mentioned to you in terms of cabin air process applications, the fire detection and pollution control, process of explosives, logistics and perishables. So miniaturized, low cost, high performance, low power. This is the kind of demand. I come from the aeronautics area, so I certainly would like to talk about what is called the MIL version. We were always taught in our classes that for aero and defense applications you use MIL versions. And in those days when we started learning, it was this word itself was. So we used to say, I hope MIL is being supervised in a big manner. But in the case of MIL, as far as these silicon devices are concerned, DO-254 and MIL compliance, high reliability and safety becomes critical. Inbuilt redundancy, radiation hardening for the space systems, thermal and mechanical, and robustness, high performance analog components. This is what is the demand, the requirement from all of us. And the main thing in here is high reliability and safety critical. So we have virtualized certification to be done, model-based engineering, key standards and IP support like MIL STD 1553 or DOT54 or verification IP in that case. Identify worst case behavior, performance and fault handling. FPGA-based systems mainly finding place where relatively low IC volumes versus commercial result in FPGA-based end products, FPGA capacity and performance challenges and so on. Size and weight, of course, is a major requirement in terms of swap. Trusted supply chain, as I mentioned to you, security is a major problem. So recognized leadership for design, verification, and implementation is a must. Validated semiconductor IP that integrates into design effectively, and proven solutions to support the foundries, microelectronics, trust compliance. Of course, system design gives you the complete requirement. In the case of IoT, this market is going to be huge, and we are already seeing the world population going to 7.6 billion, and the connected devices changing from 500 million to about 50 billion. And connected device per person used to be 0.08 once upon a time, and today it is reaching to almost 6.58. So you can imagine the kind of market which is emerging. In terms of the kind of connections, you have IoT as devices, which are the smart devices, the aggregation layers, hubs and gateways, and the remote processing, the cloud-based systems. So things with sensors and actuators that monitor and control. So it is all functions in that. Connectivity and interfaces to aggregate the as data to send to the cloud, and applications to analyze the data and offer cloud services. This is the demand. You see the market features and the deep machine learning. That is what on the one part. The process technologies from 55 ULP to as much as 28 2x times ULP and SSD RAM. Wi-Fi, Bluetooth, cellular, USB, all of them transforming. And most of the NVM memories, which are going to embedded and MRAM and ReRAM and PSRAM. This is the kind of transformation which is taking place here. What foundry offers for IoT are different things. For example, IoT smart analog, the 55 ULP RF EF technology, E-flash, 40 ULP in the 40 nanometers, then 28 HPC, and then 16 to 14 nanometers. In the case of initial one, the integration mode is mixed signal, embedded NVM integrator. In the case of 28, you have lower cost and more functionality, and node is selected mixed signal and RF and external memory. And in the case of the 14 nanometer, that is 16 FFC, you get hubs, display, audio, vision, all of them. Now, these are the kind of things which are being offered for the IoT even today. The most important thing which is emerging and which I love to do, in fact, I have been pushing that in India, photonics-enabled VLSI. And that is what you can see here when you have a photonics-enabled VLSI, where on the top layer you have 3D memory, you have a many-core systems, you have a cache, you have a 3D SSD, and then you have a transpose layer, what we call a silicon optical transposer. And below that, you have all the silicon optical modulators, germanium photo detector, and so on. What is needed from a 2-inch what has been shown here to 19-inch is what is requirement. The process interconnection, the multi-core to many-core. Memory interconnection from flat memory to 3D memory. To storage interconnection, which is HDD to 3D SSD. And peripheral interactions, which is HDMI to Super High Vision. And server interactions, which is exascale computing. So these are some of the semiconductor challenges when you want to do photonics enabled VLSI, which is what we are going to we need today to reduce the kind of latency what we have in systems today and make the systems more and more efficient and in terms of power minimum requirement. To summarize, the silicon technology is going from 50 nanometers to 2.5 nanometers to integration to ultra micro robot, mind reading ubiquity, every space being information sending source, concurrent sensing. So there's a safe towards convenient, towards era of friendlier and more natural interfaces. Then integration with bio nanotechnology, and that is what is going to happen in around 23 times when we go beyond the nano capsule and so on. So this is a roadmap, nanometer world open by ultimate integrated technology, silicon technology roadmap, and we say where miniaturization, performance lower, and power consumption lower. This will continue to be the driving force. But you will reach 1 nanometer one day, atom and molecular control space. which will meet the complete requirement. So you have a spin device, CNT transistors, interface with molecular device, and micro boards. That is what is going to happen by about 2040. So the world of 2030 will have certainly the core technologies, which will be the leading edge technology, and advanced lithography, critical FUL and BOL solutions, material challenges, advanced packaging. Then you will have customer satisfaction in terms of in terms of lower energy consumption, emerging memories, storage, and so on. But most important thing is the applications which is going to support, like automatic operations, smart societies, and so on, through the interface, which is the emerging technologies of AI, deep learning, advanced architectures, as was being told earlier, when the machine learning will aid to the designing process, neuromorphic computing and things like that. So rapid growth in semiconductor applications in a range of areas, more sophisticated technology requirements are emerging tomorrow. So to say that, just for example, brain of a mosquito make the real-time 3D flight control with image processing equipped with many sensors such as infrared and carbon dioxide, with extremely small brain volume and extremely small energy consumption. The performance of dragonfly's brain is much higher. Today's performance and energy consumption of the microprocessor are not comparable to those of insect brains at all. So introduction of the algorithms of the biosystems will be the ultimate method in the roadmap that is going to come. I want to conclude this with the slight idea I want to give about what's happening in India. We of course have we want to have a 40 nanometer FinFET technology and so on. Cost of the fab setup is going to be more than 8 billion. What we have today on the right hand side is 180 nanometer CMOS technology node with 8-inch wafer, with SCL Chandigarh is doing. We are providing VSL design services, fabrication support, and so on. But what we are looking for is integrated chip design, fabrication, and testing, and that's why Government of India has sent expression of interest for the international communities to come and work with us in India in setting up foundry, where fabrication of chips in existing 180 nanometer CMOS technology for specific design of India and worldwide. Then we want to have a public-private partnership in setting up much more high resolution foundries, along with the design, fabrication, packaging, and testing, and of course establishment of electronic packaging and automatic testing facilities to support the chip manufacturing ecosystem globally, for which Government of India strategy for self-reliance, as we call it, Atmanirbhar in electronics and semiconductor. We intend to have what is called the National Institute for Semiconductor and Electronics Research, about 10%, $3 billion. Then we want to have products, electronic systems, and fabless chips and ICs, which we want to spend about 20%, about $6 billion. And then manufacturing, electronic systems, semiconductors fab, about $21 billion. So about $30 billion US Government of India investment over 15 years is what plan, and you will have skilling and manpower development as part of it, infrastructure, raw materials, and things like that. So there is an opportunity for international collaboration. All the foundry companies, all the system designers across the world are most welcome to shake hands with Indian designers and Indian companies to set up this kind of a semiconductor ecosystem in the country. Most welcome. I request that this is an opportunity, and this seminar should certainly help us in collaborating with the best in the world to take the phase of semiconductor design, development, and manufacturing to a level which is better than what is existing in the world, and we become a leader tomorrow along with the other partners. Thank you very much for inviting me. Thank you. And these are some of the conclusions, but I think these are basically same. But what it says is CAGR of 20%. That is what kind of growth is going to take place. Thank you. God bless you.
Thank you, sir, for such a deep, insightful vision about Government of India, and giving, an insight from the beginning and the whole, walking us through the whole of the history of semiconductors. So with this, I have, as like all speakers, huge set of questions from each category, students, academia, industry, lined up for you. But I would, in the interest of time, I would like to just pick up one of them, which came very prominently from multiple delegates, that this whole vision of having our own fab, our own manufacturing, a commercial manufacturing facility. Do you see this getting realized in next 2 years, 5 years, or 10 years? What is the timeline which you foresee in your present capacity?
I foresee that with the kind of investments which are being identified today, 5 to 6 years is the time period I am putting for India to become good as far as commercial fab is concerned. But even before that, I see a couple of ATMPs coming up and a very strong fabless foundry ecosystem. That is what is going to emerge. In addition to the electronics product manufacturing. This is the kind of a roadmap with the Ministry of IT and Electronics we have worked out. And with the major push which is taking place on the National Supercomputing Mission and Indian Microprocessor System, I think this will see the reality. And I have no doubts what is needed is at the moment collaboration. So if we can get a right collaboration, the speed will be right.
Great, sir. Very well articulated, sir. Looking forward to this, manufactured in India wafers in our, respective markets. So thank you so much for taking out time from your busy schedule and, enlightening us with your vision here. On behalf of the conference and the society, VLSI Society of India, I thank you for your time. This is a small virtual token of appreciation for you, and we'll be sending a physical one to your office. So thank you so much. Thank you, sir. So with this enlightful talk by Dr. Saraswat, we have come to the end of the inaugural day session, the inaugural day keynote talks. We'll now move to parallel sessions, session 1, 2, and 1A, 1B, and 1C, which would be run in parallel. You need to visit the respective session and join the link, and you'll be able to hear the technical paper presentation. And then we'll move for a lunch break from 12:30 to 1:30 hours. And post that, we'll meet again in session 0, this common session, for the next keynote talk and panel discussion. With that, I again thank you all for your time, patience, and your valuable questions for making this conference interesting and interactive. And we'll close this particular session, and we'll meet you in the other parallel sessions, 1A, 1B, and 1C. Thank you again. Thanks.